Good morning and welcome. We are Team 26, and we are currently working with General Dynamics on a photonic downconverter, which would hopefully have an end application to space, but it's going to be a more cost-effective solution compared to what's currently on the market. I'll give you a quick top-level overview of what a downconverter is. Downconverters convert radio frequencies down into a more easily read intermediate frequency. This is done by combining the radio frequency with the local oscillator, and it's a process called frequency conversion and/or heterodyning. But now, our application uses an optical signal. This process changes slightly in the sense that now we implement a modulator that is going to be used to upconvert the signal to the optical domain, mixes it with the radio frequency local oscillator, and there's going to be a photodetector also in place that helps downconvert the RF signal to the desired intermediate frequency. So there are many benefits of using the optical downconverter over a standard downconverter, such as like a larger bandwidth capabilities, immunity to electromagnetic interference, and a higher isolation between the radio frequency and the local oscillator. So continuing on, I will pass you over to William, who will cover the block diagram and the analysis which we have implemented, to Link for the MATLAB, finally to Danielle for why we have characterized the parts.
The team developed a block diagram to show where all signal inputs would go through each component. We later discovered that the FPGAs and circulators wouldn't be necessary, however the additional amplifier was needed to overcome the loss of signal power. We developed two analyses, one for predicting power levels and one to make sure that damage prevention.
The system was modeled and simulated in MATLAB. This allows for a proof of concept to be obtained and for pre-data to be collected and compared against the physical build to see if we are getting reasonable results. This model went through 4 iterations. First, a series system was created, then a basic parallel system. The parallel system was then broken down into sub-functions for ease of use, and finally we added complexity into the sub-functions to get a more accurate result. This led to a discovery that some components weren't needed in the system and other easier to work with components could be used in their stead.
The first step of testing is parts characterization. This allows us to input accurate values into our MATLAB model, as well as verify that the parts are working as expected. It was important for us to test our photodiode against the laser because we wanted to make sure we stayed within the safe voltage levels for the diode while still providing the system enough power through the laser input for the down conversion to be successful.